Okay, so now in curve sketching we're going to look at increasing and decreasing tables and concavity charts, which is just, these are just factor tables for inequations really. So we're going to look at first is this problem here. We're going to try and sketch this cubic that we already know how to sketch, most of it. Basically if it's factored it looks like this. If I was to give it to you in non-factored form it would look like this one here. And then you'd have to factor it by just taking the common factor of x out. To take the derivative, you can either use a product rule, or you can take the derivative from here, which is what I chose to do. So the derivative from this point is here. Now, to determine when a function is increasing or decreasing, you're just looking at the slopes of the tangents of the function. Because when a function is increasing, for example, like this, so that function is increasing all the time. If you look at the tangents on there, they're always positive. The slopes are always positive. Okay? So when we're looking at when a function is increasing, we're looking at when the derivative is greater than 0. And so if it's decreasing, then that means that the slopes of the tangents are negative and the derivatives are less than 0. So we're really solving some inequations here. Okay, so for this one, when a function changes from increasing to decreasing, it's probably going to do something like that, where the slope of the tangent is 0. So where it goes from increasing to decreasing, it's going to have to pass through 0 most of the time. So you want to find the zeros of the derivative. That's not all of them. It often happens too where you could have a function that is increasing here and then decreasing, like the function 1 over x squared. So that's increasing, the derivatives are positive, and then decreasing, derivatives are negative, but it's not around a max or min, it's actually around a vertical asymptote. So this would be a x equal to 0 would be a critical number for this chart that we'd be looking at as well. And that would mean that basically you have a factor of x on the bottom. Okay? So in this example here, we've got f prime of x set to 0. We can do this in a couple of ways to get x equal to 3 and negative 5/3. So by using the quadratic formula or by factoring. Okay, so when you factor it, you get 3x plus 5 times x minus 3. And you can graph this cubic. The only thing we don't really know is where are the maxes and mins. And so this is going to tell us a little bit about that for the max and mins. Basically they're going to happen at 3 and negative 5/3. Okay, so we call 3 and negative 5/3 a critical number. Okay, they're critical numbers. Those are two of the numbers that we're going to use to break up the whole number line. And I'm making now from this a concavity, or not a concavity, a chart that is an increasing decreasing table. Okay, so here is the increasing decreasing table. Basically you're taking the factors of f primed, or just f primed if you can see it. It's a quadratic, so you can jump right to this one right here. Okay, so this factor changes signs at negative 5/3. And it's a line that has a positive slope of 3. And so it's negative to the left of negative 5/3 and positive to the right. So if you're to graph y equals 3x plus 5, it would look like this graph over here. And you can see that the value of 3x plus 5 is negative to the left of negative 5/3 and positive to the right. So where this changes signs is that where it is 0, and you can just plug negative on that side, positive on that side. You don't even have to sub numbers in. This factor here changes signs at x equal to 3. Okay, because x equal to 3 makes it 0. It has a positive slope, so it's going to be negative on the left side, positive on the right. Or you can just jump right down to f prime, which is this quadratic here. You know what the zeros are of it. you know the quadratic opens up. So the quadratic is going to basically look like, so at negative 5/3 and 3. So it would look something like that. So you know it's going to be positive here to the left of negative 5/3. Okay. And negative between 5/3 and 3, negative 5/3 and 3, and then positive again on that side. So you could just jump right to that if it's a quadratic. Okay, but this is what we use for more complex ones, and we're going to use this model to move forward with. Okay, so that's the increasing decreasing table. So if f prime is positive, then the f of x, the function f of x, is going to be increasing. So we use this arrow for increasing. Then f prime is negative, decreasing. And then increasing when it's positive again. So this tells us what's happening to the function f of x, which is what we're trying to analyze. And if it's increasing, then decreasing, we must be hitting a local max there. And then it's decreasing, then increasing, we must have had a local min here. So how do we find these local maxes and mins? Well, the local max and mins are the y values. So we're going to plug those into the original function, and what we get is these values here for the local max and this one here for the local min by plugging it into the original function. And so far what we have then is this graph here. Okay, so we have the x-intercept is negative 3 and positive 5 and 0 from the original factored form. Okay, so from this form here we get the zeros of the function. And then we have the local max, which is here at negative 5/3 where the derivative is 0, and local min where the derivative is 0 at 3. Okay, so the min is negative 36. The local max is 14.81 approximately. That's what we have so far for the increasing decreasing part of this. They get more complex. We're doing this on a function that we know so that we can see how this works. Now the concavity chart. Okay, so as we've discussed before, concavity, when f of x is concave up, the slopes of the tangents are increasing. Okay, so for a function that is concave up like this, the slope of the tangent here is negative, 0, then positive. So the slopes go from negative to positive, which means it's increasing. If a function is increasing, then its derivatives are positive. So the slopes of the tangents are the derivative. If the derivatives are increasing, the second derivative is positive. So where a function is concave up, that is where the second derivative is greater than 0. Okay? Now, same thing applies for when the function is concave down. The slopes of the tangents are positive, 0, then negative. So they're decreasing. So the second derivative is less than 0. Okay, so continuing that last example, let's take a look at the second derivative now. The second derivative is 6x minus 4. So 6x minus 4 is very easy to solve. If something is going to go from negative to positive, it's either going to go by an asymptote or it's going to go through 0. So let's see where this is 0. So you plug that in to 0, equal to 0, you get x equals 2/3. So at x equal to 2/3, the second derivative is 0. See if it changes signs on either side. Okay, so we're solving this inequation where f double primed is greater than 0 or less than 0. Okay, so we're going to do a factor table for this. It's very easy. It's a linear factor. Okay, so I'm writing it out. It has a positive slope, so it's going to be negative to the left of the 0, positive to the right. It's a linear factor. So that is f double prime. So f double primed is negative, positive. Because it's negative, it's concave down. It's less than 0. It's concave up here. Okay, so 2/3 is a critical number for the concavity chart. Okay, so not for the increasing decreasing table, just for the concavity chart. Now, because this is changing concavity, and the function exists at 2/3, we have an inflection point there. Okay, so now this concavity chart helps us to determine when we have an inflection point. Inflection points happen when there is a change in concavity. Okay, and the function exists there. So here the function exists at 2/3. It's a cubic. It exists everywhere. Okay, and so it has an inflection point at 2/3, at x equal to 2/3. So now we can state these important points that we've got. We got the local max, which we calculated earlier, is 14.8. The local min, which is at 3, -36. And the inflection point. So subbing 2/3 into the original function will get you approximately -10.6. Okay. So those are the important points that we've got so far. Now we can take a look at what graph this produces. Okay, so the graph that this produces is right here. Okay, so we have the local max, which we talked about earlier. It's at -5/3, not right in the middle of -3 and 0. Okay, the local min, which is right here at -36. The inflection point, which is at 2/3, -10.6 on the y, so right in there. So it changes concavity down, from down to up. And this is a more accurate graph of a cubic than we could have done in advanced functions, because now we have the local max, the local min, and the inflection point.